Hello, I'm presenting on a rain episode that impacted Greenland last August 2021 in context of albedo feedback, absorbed sunlight, and I'll touch on the snow line, like you can see here, this amber color, which separates snow cover above and bare ice below. Turns out that the variations of snow line in concert with mass balance point to the actual imbalance of land ice. This project, and you can see a daily animation of albedo from land ice areas in the Arctic, 8 regions. We're also looking at Alaska, Norway, and about to expand to parts of Antarctica. Theoretical basis published in Cryosphere, Remote Sensing, led by theoretician Alex Kokanovsky. And we call this effort Snow and Ice Optical Properties from Sentinel-3, or SICE for short. And the study I published 20 days ago finds that the driver of the rainfall that was witnessed at the highest point of the ice sheet was an atmospheric river. That's a concentrated poleward flow of heat and moisture. And this produced the largest rain extent on the Greenland ice in the last 40 years, at least. Field workers observed this ice crust, and surprisingly, there were no rain gauges running at Summit Station. I'm sure there are now. And anyhow, using a lot of Earth observation data and field data, you can see a Sentinel-3 color image in the background below the Sentinel-2 images that show flooded snow conditions, very dark, and it's really uncommon to see such dark blue snow over such a wide area of Greenland. We independently gauged the melt impacts using runoff at a river at the bottom side of this catchment here. Weather stations CAN, L, M, and U. DI2 is even higher. And Nuke U down here. And so this box on the map shows that area of interest, and that where we average the albedo data. The pink colors, the dark pink is 2 days of AMSR 2 melt extent. The light pink was the 1 day snapshot of melting, which are wet snow conditions, which were evident at Summit. We backed out a 3 millimeters rainfall from the thickness of that photo of the ice crust as part of this publication. Since 2018, we're starting to integrate a rain gauge onto the PROMICE stations. This is Nuke U. And last year on the new generation of GCNet stations led by Gaius, we actually have 2 rain gauges. And so we have an equivalent temperature humidity measurement at these 2 levels from which to compute vertical turbulent energy fluxes. And so the field data and the EO SICE albedo are shown here before the atmospheric river impact. So you have relatively high albedo at CAN-L, about 0.5, and then up in the snow area, we observe albedo around 0.8, and it's in agreement with the field data. Nice to see the satellite retrieval agreeing well. And then the next period is from the 15th to the 19th of August. This is after the impact, which was on the 14th of August, and a huge reduction in albedo across the ablation area. It pushes the bare ice area up by 750 meters. And again, we have agreement with the ground data. The study ends up focusing on the upper elevations of the ice sheet where there is a pretty consistent 0.1 decrease in albedo. So it gets darker by 10%. It's a wide area. And so this translates into quite a lot more energy absorbed by the ice sheet. And at one of the high prom ice stations, 1,840 meters, well up in the accumulation area, the various components of the energy budget are adding up to a melt energy. It's positive, meaning energy is directed toward the surface. So this is heating the surface, producing melt. And turbulent energy fluxes were dominant during the atmospheric river. And you can see a reduction in albedo that continues dropping because the surface is melting more. The grains of the snow are growing. And then you get clear sky conditions. You can see the shortwave energy fluxes are quite high, and the melting continued. And this was the albedo feedback phase. So the initial perturbation, it darkens the surface. And even though at nighttime there was sub-freezing conditions, there was daytime melting that was sustained. And that's illustrated here by the cumulative melt, which was strong during the short-lived atmospheric river impact. And then here's this later clear sky albedo feedback phase. And had the albedo stayed at snow values, the melt would have been lower. And so we estimate the albedo feedback empirically, and it adds about 30% more melting. And the cumulative melt here, 36 millimeters, is higher than during the short-lived atmospheric river. So had the AR not happened, this feedback phase would not have happened. It also was important that it got clear skies. So this is an example of albedo feedback. And when you get into the supporting information, then I put both documents in the presentation folder. So please have a look at the supporting info and go ahead and grab the PDF of the article because it has a couple of typos corrected in it. And here lower at 1,269 meters, it's actually a bigger story, and it doesn't really come through so much in the paper because we focused high on the ice sheet. But here you see, again, a dramatic reduction in albedo from 0.8, because it actually snowed before this as part of this weather system. But that snow is erased. Bare ice and flooding conditions bring albedo down to just above 0.2. This is a huge reduction in the brightness of the surface. It stays dark, and the melt energy continues. Had snow cover remained, the melt would have been about half as much, or 50% less than this value. So again, it demonstrates a very strong impact of an extreme event late in the melt season. It's extending the melt season. And in the last 3 slides, I want to talk about the snow line. So we can separate the snow-covered area, the bare ice area, using Sentinel-3 optical imagery. And here's an example of a low melt year where you have a relatively high accumulation area ratio. So the white area is relatively high as compared to the total area. In a high melt year, you have a lower accumulation area ratio, AAR. So AAR is a concept that's been worked with in glaciology for some decades, and we're applying it because it points to an equilibrium condition. When you plot mass balance here from GRACE and regional climate models, a variety of data sets can give you mass balance from Greenland on an annual basis. Here is the accumulation area ratio. And for these different years, for example, the high melt year 2012, it has a low AAR. The low melt 2018 has a high AAR. And this scatter points to an equilibrium where you have an intercept of AAR and mass balance. And based on this equilibrium condition and the actual sample of observations, the ratio of, say, the average to the equilibrium is the fractional imbalance of the ice sheet. To readjust to this perturbation, the ice sheet's equilibrium line climbs up to, well, here is the equilibrium ELA equivalent with the equilibrium AAR. The equilibrium line altitude, it moves up in a warming climate. You have a larger bare ice area. And this new ELA is associated with a shape adjustment necessary for the ice sheet through its own dynamics to be in equilibrium with this new climate of the past 20 years. Implicit in that is a volume reduction and an area reduction that's equivalent with 3% of the area and volume. We use a very conservative scaling to get by issues with piracy between flow sectors. The actual value, which is empirically determined from bed machine, is 1.25 higher in the exponent. So the more likely imbalance is higher than this. But to get it through review in Nature Climate Change, we went with this ultra conservative lower bound rock bottom estimate, which is equivalent with 270 millimeters of committed sea level rise from Greenland. And of course, as the climate warms up, if we use 2012 as an analog, the sea level commitment climbs quite a bit, 780 millimeters of committed sea level rise. In the condition that climate doesn't cool, or climate stays at least at this 20-year, past 20-year, we call that the present climate, the ice sheet is committed to ablate. And this should be coming out in July in Nature Climate Change. We're just working on the technical side of the final checklists of this document. And so the use of EO data, optical, and say gravity can be combined to estimate committed loss from land ice areas that have a varying equilibrium line that's visible. There probably are some questions in your mind about tidewater glaciers, and we've accounted for that in the study using an effective ablation area. So thanks for your attention, and have an ice day.